Today we're going to talk about something called a definite integral and also the fundamental theorem of calculus, which, as you can tell by the name, is a really big deal in calculus. It's one of the biggest theorems we have in all of calculus. So first, let's talk about what a definite integral is. Well, first, remember that earlier we talked about finding the area underneath a curve. So recall that we had the area under a function f of x on an interval was given by the limit as n goes to infinity of the sum from 1 to n of our function with some values xi plugged into them times delta x. And we used this when we were taking our interval and dividing it into n equal pieces and estimating by adding up the areas of the rectangles that were made up by those n pieces. But there's nothing requiring that we have to divide our interval up into rectangles of equal width. So let's start by talking about what happens if we divide it into unequal widths. So, start with a function f of x defined on the interval AB. And divide the interval AB into n subintervals with partition points a equals x0, and then I have x1, x2, all the way through xn, which is equal to b. And we have that x0 is less than x1 all the way through xn. So I'm just chopping my interval up into n pieces. The only thing though is I'm not requiring all the pieces to be the same size. So these subintervals are called a partition of our interval. The subintervals are x0 to x1, x1 to x2, all the way through xn minus 1 through xn. They are a partition P of our interval AB. So you have a partition when you just chop the interval up into pieces, but the pieces don't all have to be the same size. They can be, but they don't have to be. So since we're not assuming these are the same size anymore, we're going to choose some new notation, delta xi, to be xi minus 1, which is the width of the ith subinterval. Then I can choose a point in each subinterval, plug it into my function to get the height of that particular rectangle, and we can add up all of these areas of rectangles, which aren't going to be all the same width, but they're still areas of rectangles. So choosing a point, xi star, in the ith subinterval, we have the sum from 1 to n of xi, f of xi star times delta xi approximates the area under the curve. So this really isn't any different than what we did before. We're just writing it even more generically so that we can have our interval divided up any way we want. Instead of just into equal strips, we can have strips of any size. Then I can define something called the definite integral, which gets me my exact area under the curve. So the definite integral of f from a to b is the number given by this notation. Integral with an a and a b on it of f of x dx. This is defined to be the limit of our sum that we got using our generic partition. And this limit is as the maximum of our delta xi goes to 0. So earlier when we were dividing into equal size strips, we had this limit as the number of rectangles goes to infinity. Now I can't really say that anymore, because what if I had one really huge rectangle in there and the rest were infinitely tiny? I could still have infinitely many rectangles, but have a very bad approximation if one of my rectangles is huge and doesn't really get any smaller. So this notation here is saying the maximum width of my subintervals is going to 0. It's the same idea, and in fact, if I actually choose all my subintervals to be the same width, this is equivalent to having infinitely many rectangles. So it's still the same idea. Chopping it into more and more rectangles, and we are chopping it so many times that the rectangle with largest width has width going to 0. Then this gets us our exact area, and we're calling it a definite integral. So normally we do nice partitions where the widths are equal. This was just to show you it doesn't have to be equal. So if we choose a partition with equal width subintervals, like we had earlier, then our integral from a to b of f of x dx is equal to the limit as the number of rectangles goes to infinity of the Riemann sum that we were using before. And that's usually the one that we use. So the first thing we're going to do is I'm going to give us something that looks like this side, and we're going to write it in this new notation. And pretty soon we're going to learn some other things to help us evaluate these definite integrals, so we won't have to do the sum all the time, because that is very, very tedious to have to do that. So, first example. Let's express this sum, the limit as n goes to infinity of the sum from I equals 1 to n of xi to the third plus xi sine of xi delta x as an integral on the interval 0 to pi. Well, this is a lot scarier looking than it actually is. To figure out how we're going to write this integral, I know I'm going to have my integral symbol and I'm going to have two numbers on it. Those are my a and b for my interval. So on this problem, I'm going to have 0 and pi. So there's my integral from a to b, which is integral from 0 to pi. Then here I have f of x. And how do I find f of x? I look inside my sum and I just write what I have, but without all the i's. So I have x cubed plus x sine x, and then I need at the very end my dx. And now this sum with a limit is written as an integral. And at this point, we still don't really know how to evaluate this, but we're going to learn how to do that, I believe, yeah, on the very, very next thing that I write down. So it's going to be much easier. We're not going to have to write it all out as a sum and take the limit. All right, so let's get us our first extra bit of information on how to deal with these definite integrals. All we know so far is that they give us area. This is part of the Fundamental Theorem of Calculus. There are two parts to this theorem. And this is the first part. It says, if f is continuous on the interval AB, then the definite integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where f is any antiderivative of little f. So what this is saying is if you're going to be trying to evaluate a definite integral, you can find the antiderivative of the function and then plug those values into that antiderivative, and that will get you the area. Let's do some examples of these definite integrals. Our first example actually evaluating a definite integral from 0 to 1 of x squared dx. So I know from that Fundamental Theorem of Calculus Part 1 that I need to find an antiderivative of this x squared. We can do that by adding 1 to the exponent and dividing by the new exponent, which is the same as multiplying by the reciprocal. Now I'm going to show you the standard notation that is used. You either use a vertical line, or some people like to put little brackets on it like that, but I tend to just use a vertical line. And you put your numbers on it to say we're going to plug these numbers in. We know from the theorem that you're supposed to plug in the b first, so that's plug in the top number, and then plug in the bottom number, and there's a minus sign in between. And when I evaluate this, I get 1/3 as this area underneath the curve x squared from 0 to 1. You might recognize this one from before. We had done this one previously, but doing it the complicated way. And now this, honestly, is much simpler. Now, some of you might be wondering, though, when we were doing indefinite integrals and finding all our antiderivatives, we always had that plus c, and it was a real big deal. Why didn't I use a plus c on this particular problem? And the answer to that is because I didn't need it. The Fundamental Theorem of Calculus says any antiderivative will work, so I just happened to choose the one where c was 0. Would it be wrong if I used a plus c? No. If I had put a plus c in here, I would have had a plus c here and a plus c over here, but it's being subtracted, and the c's would have canceled out anyway. So as long as you're careful with subtracting, the c's should take care of themselves, but it's standard just to not even include the plus c, because it will cancel out anyway when doing a definite integral. So let's do another one of these examples. Let's find the definite integral from -2 to 1 of x to the third dx. Again, I need an antiderivative, so we add 1 to the exponent, divide by our new exponent, and I'm going to plug in my numbers. You always plug in the top number first, and then subtract what you get when you plug in the bottom number. And now it's just a matter of simplifying. I have 1/4 times 1 to the 4th, so that's just 1/4, minus a 1/4 times a -2 to the 4th, that's 16. So this is 1/4 minus 4, which is a -15/4. So I got a negative area under the curve. All that means is that this graph on that particular interval has a lot of stuff beneath the x-axis. We consider the area above the x-axis to be positive and the area below the x-axis to be negative. All right. So that was our first couple examples of definite integrals, and that wasn't too bad. Let's do one that's a little bit harder, but still not terrible. Let's try definite integral from 0 to 3 of x to the third minus 6x dx. So this one's just a little more complicated because I have more terms. The biggest danger with that is being careful when you're subtracting using the fundamental theorem of calculus. It's very easy to forget to distribute your negative sign. So first, find your antiderivative. Antiderivative of x to the third, I add 1 to the exponent and divide by the new exponent. Now for the minus 6x, I'm going to add 1 to my exponent and divide by that new exponent. That's 6 divided by 2 is 3. Now I need to plug in my numbers. I would suggest you put a gigantic set of parentheses around the values that you get when you plug in the top number and the bottom number, just to be careful with that subtraction. So here I'm plugging in the top number, and then I'm going to plug in the bottom number. Now, everything in this second set of parentheses actually ends up being 0. So I didn't have to worry too much about the subtraction because it's just going to be a 0 over there. So I just have to simplify this guy to finish it up. And what I will get is 81. Oh, this should be a 4th power. There. 81 over 4 minus 27, which when I simplify is negative 27 over 4. All right, so that's how we evaluate definite integrals using our antiderivatives. I don't think it's too incredibly terrible, and we're actually going to do another couple examples of that before we move on to our next bit of information for this video. So 2 more of these. How about the definite integral from 0 to 12 of x minus 12 sine of x? So this one we're going to have to remember one of our trig antiderivatives, but I think we can do it. So first, I need to do the antiderivative of x. That's a power rule. Add 1 to the exponent, divide by the new exponent. Now for this minus 12 sine x, I know the antiderivative of sine would be negative cosine. So this minus actually becomes a plus, and I get 12 cosine of x. And then I need to plug in my 12 and my 0. So I'm going to plug in 12. And then I'm going to plug in my 0. And simplify. So 12 squared is 144, and half of that is going to be 72. And then I have 12 cosine of 12. Don't try to simplify that. 12 is not on the unit circle, so I'm just going to leave it as 12 cosine of 12. Over here, I get a 0, but then 12 cosine of 0 is 1. So this guy is 12, and I'm subtracting it, so I get minus 12. So when I put that all together, my 72 and my minus 12 get me 60, and I still have 12 cosine of 12, whatever that is. Okay, so that was our first one with trig. Still wasn't too bad. It's still the same idea. Find the antiderivative, plug in the numbers, simplify. All right, let's do one more example before we move on to the next bit of information. This one's going to be our hardest one so far. An integral from 1 to 9 of 2t squared plus t squared square root t minus 1 over t squared dt. And I would suggest that we solve this one by splitting it into 3 different fractions first, because we should hopefully be able to simplify with our power rule. So I'm going to split it into 3 different fractions. And then I can simplify within my integral. I get 2 plus a square root of t, which is t to the 1/2, and minus a t to the negative 2. And now this I can evaluate just by using my power rule, so it's much simpler. So finding the antiderivative of 2 is going to be 2t. For this guy, I have to do my power rule, so I add 1 to the exponent and divide by my new exponent, which is the same as flipping and multiplying by the reciprocal. And again, I'm going to add 1 to an exponent and divide by the new exponent, which is going to change this minus sign into a plus. Then I just need to plug in my values, a 9 and a 1. So I'm going to plug in the 9 and get 2 times 9 plus 2/3, 9 to the 3/2, plus 9 to the negative 1, that's 1 over 9. And then I'm going to subtract what I get when I plug in the 1. 2 times 1 plus 2/3, 1 to the 3/2, plus a 1 over 1, which is 1. So now I just have to simplify. I get 18 plus my 9 to the 3/2 would be 3 cubed, which is 27. 27 times 2/3 would get me 18. And I still have my 1/9. And then in my second set of parentheses, I have a 2, so minus 2. This guy is going to be minus 2/3 and minus 1. And then I just have to combine all of that together, getting a common denominator when necessary. And when you do all of that adding and subtracting, your final answer should be 292 over 9. All right. right, so that was a slightly more complicated definite integral, but notice that it was still the same exact techniques as what we did on the easier ones. All right, so now we need to talk about some properties of our definite integral, and then we finally get to move on to the second part of the fundamental theorem of calculus. But first, the properties. So we have quite a few properties of definite integrals. The first one says the definite integral from a to b of a function is the opposite of the definite integral from b to a of the same function. So this is saying you can switch the order of the bounds of integration, but if you do that, it changes the sign of the integral. I personally never really rearrange the order of my integration. I just do it as written most of the time, but it's still good to know this property. Another property, if you have a definite integral from some number a to itself, that's going to be 0. If you think about it with the fundamental theorem of calculus, this makes sense. If I did the antiderivative and plugged in a and then a with a minus sign in between, it would subtract to 0. Third property, if you have an integral from a to b of some constant with respect to x, you just get the constant times b minus a. And you could get that one without even memorizing a property. Just find the antiderivative of the constant, plug in the b and plug in the a, and you'll get the same result. Property 4 says that the definite integral from a to b of f plus or minus some other function g is equal to the definite integral from a to b of f plus or minus the definite integral from a to b of g, which works out exactly the way we would want it to. We also have a property that definite integral from a to b of some constant times a function is the same thing as the constant times the definite integral of the function. So you can pull your constants out in the front. This is something that I think is usually a matter of personal preference. I personally usually leave my constants inside the integral, but I know a lot of people really like pulling them outside of the integral. Figure out what works best for you and do it that way. I personally don't really like pulling my constants out because then I tend to forget that they're there and then I get the wrong answer at the end. Other people think it makes it easier when they don't have the constants cluttering everything, so they pull them out because it's easier for them. Do what works for you. Last few properties before we do an example. This property is very useful. It says the definite integral from a to c of f of x plus the definite integral from c to b of f of x is equal to the definite integral from a to b of f of x. So notice I went a to c and then c to b. You can combine it together into one integral from a to b, as long as that top one and that bottom one match each other for the bounds. The last two properties. If you happen to have an even function, so it's symmetric across the y-axis, then the integral from negative a to a of f of x is going to be exactly equal to 2 times the integral from 0 to a of our function. So this is saying if you're symmetric about the y-axis, you can find the area of 1/2 of your integral. That was really bad description. You can find the area of half of the picture and multiply the result by 2, as long as it's symmetric about the y-axis. And in order to be symmetric about the y-axis, you have to have an even function. And the last property, if f is an odd function, then the integral from negative a to a of f of x is 0. So when you're an odd function, you're symmetric about the origin. So that means you have rotational symmetry. And if that happens, you end up getting an integral that equals 0. All right, so let's go ahead and do an example using some of this information. If the integral from 0 to 10 of some function is equal to 17, and the integral from 0 to 8 of that same function is equal to 12, find the integral from 8 to 10 of that function. So notice here, I don't even know what the function is. So I can't just look at what they're trying to have me find and do an antiderivative and plug in the 10 and plug in the 8. I don't even know what this function is. I'm going to have to use the properties of my definite integral to figure out what this last integral is equal to. So what I know from our properties, it was property 6, I believe, on that list. We know that the integral from 0 to 8 plus the integral from 8 to 10 should be equal to the integral from 0 to 10. Because I have this 8 and that 8 are matching on my bounds. So notice this guy right here is the one I'm trying to find, and the other two are the ones that they gave me information about. So they plug in everything I know. 12 plus the integral that I'm trying to find equals 17. And so I can find that my integral from 8 to 10 is equal to 17 minus 12, which is 5. All right. Three more quick properties. If we have a function which is not negative for all x between a and b, then the definite integral from a to b of our function is not going to be negative. Also, if we have two functions and f is greater than or equal to g for all of the x values between a and b, then the definite integral of f is going to be greater than or equal to the definite integral for g. And our last comparison property says that if my function is in between two values, little m and big M, for all of the x in our interval, then I know that little m times b minus a is going to be less than or equal to the definite integral of my function, which is less than or equal to big M times b minus a. So this last property is saying, if you happen to know the minimum value of your function and the maximum value for your function on a particular interval, then you can estimate this integral by knowing it's in between these two values here. All right, let's see. I think we are finally ready for the next part of the fundamental theorem of calculus. So, fundamental theorem of calculus, part 2. Says that if f is continuous on AB, then the function g defined by g of x equals the definite integral from a to x of f of t dt for a less than or equal to x less than or equal to b is an antiderivative of f. In other words, the derivative of g is equal to f of x on our interval. So what this is saying is, if we have a function defined as an integral from a to x of another function, and I need to find the derivative of this g, it's exactly equal to this function that I was taking the integral of with the x plugged into it. Or essentially, this is just saying that derivatives and integrals undo each other, which we already kind of had an idea that that was going on. This just helps confirm it. So let's do an example using this part of the fundamental theorem of calculus. So find the derivative of g of x, which is equal to the integral from 0 to x of the square root of 1 plus t squared dt. And I know by the fundamental theorem of calculus, my g prime is going to be exactly equal to the function that I'm integrating with the x plugged into it. And that's literally all we have to do. technically, we do need to make sure that the function inside of this integral here is continuous. But yes, our square root of 1 plus t squared is a continuous function, so this theorem does apply. One last thing that we're covering in this video today, the mean value theorem for integrals. Which says if f is continuous on AB, then there exists some C in AB such that f of C equals 1 over b minus a, the integral from a to b, f of x dx. All right, so let's actually try to do this. And there is actually another way to write this as well. Let me write that way down. Or the integral from a to b of f of x dx is equal to f of c times b minus a. I got this other version of it just by multiplying both sides by b minus a. So let's do an example of this particular problem. So let's let f of x equal 1 plus x squared on the interval -1 to 2. Find any number c that satisfy the mean value theorem for integrals. So first, remember what the mean value theorem says. It says f of c is equal to 1 over b minus a, integral from a to b of f of x dx. So I need to find values for c that's going to satisfy this, where my a is -1, my b is 2, and my f is 1 plus x squared. So let's just try figuring out what it is we're trying to show. F of c is what I get when I plug a c into my function. So I get 1 plus c squared. 1 over b minus a is 1 over 2 minus a -1. And then I have an integral from -1 to 2 of my function, 1 plus x squared dx. So I'm just going to leave this left side alone right now. I have 1 plus c squared equals my 1 over 2 minus a -1 is 1/3. And now let's find this definite integral. Remember, we need the antiderivative. So I get x plus a 1/3 x to the 3rd. And I'll be plugging in these numbers. So I have 1 plus c squared is equal to 1/3 times what I get when I plug in the 2. 2 plus 1/3 times 2 cubed. And then what I get when I plug in the -1, but I'm subtracting that. So minus a -1 minus a 1/3 -1 to the third. And then we just have to try to simplify this and solve for c. So I get 1 plus c squared is equal to 1/3 times, well, this is 2 plus 8/3 plus 1, and this guy is going to be a -1, but then it's still a minus over here, so this is going to be plus 1/3. And so I get 1 plus c squared is equal to 1/3 times 8/3 plus 1/3 is 9/3, which is 3. And then I have another 3, so that's 6. So this complicated looking formula has now just become 1 plus c squared equals 2. And now I just need to find the values of c that satisfy this. Subtract 1 and take a square root. So I get c is plus or minus 1. Both of those are in my interval. So both of those are my answers to that problem. All right, so that's about it for this video today. If you have any questions, feel free to ask them down below, or if you're in my classes currently, you may ask through email or office hours, all of that. And I hope to see you guys next time.